9.1. It's simply just gonna be torque. So, one second. Oh well, actually, um, so torque is defined as the force applied to a lever arm. So I'm doing this without my book. So, let's just go off memory because I did this a few weeks ago. Um, and lever arm, I guess, can be substituted for radius. In most cases, they say lever arm because it's. I don't know why they say lever arm, but it's the radius from the hinge or the distance from the hinge. I guess would be the right thing. So let's conceptualize this idea with the door, and we'll say that there's a door right here, and we'll say that the door is handing outwards. Um, Actually, maybe that's not the best thing to display. Let's say that there's a thing right here, and let's say that as a constant arm out like this. So basically something like think of it as like maybe like a tether ball station or maybe something like stationed to the ground anchored with just a line sticking out. It could even well, I guess it can't be a ruler because one side isn't stationed down. Like a door right here, right? Like this is a door, and this is the end of the door, and this is like the bolt or the hinge that it rotates around. If you apply a force here, um, you have to times it by radius to get the torque, and that is basically how much of uh, the force is being exerted this way. So that means the closer you get to the radius, or the closer you get here, the lever arm becomes smaller, and that means the closer you get to the hinge, the less effective your push will be. So I mean that's pretty cool, and that's like I mean it's definitely applicable in real life. Um, Note that here we'll typically be given the force, but the force has to be perpendicular to the lever or to the hinge. In this case, the force has to be going this way, much like centripetal velocity, or not centripetal velocity per se. Like in uniform circular acceleration or velocity, we typically only look at the velocity vector perpendicular in order to calculate centripetal acceleration. Um, so quite smart there. And always it always has to be perpendicular in order for this formula to work. And yeah, the logic here is pretty sound. But why does it have to be perpendicular? So what would happen if, let's say, this is a door and you push inwards? I'll give you a second to think about it. No matter how much force you push with, if the bolt remains constant or if the bolt remains stationary, I guess would be the right term, it will never move because you're just pushing into the hinge. And that is the beauty of torque. So yeah, we'll typically always be giving perpendicularly. I mean, we're just taking, I guess AP physics or maybe even college physics for you guys. So it's not that difficult. Just simple algebra, just multiplying the force by the radius, which is quite simple. And if you know your formulas, remember that force is kgm divided by s squared times the radius, which is also in meters. So it's technically the formula is kgm squared so that's divided by s squared. But this is not a joule, so don't get confused. Those are two different things. Now, before we continue any further, I want to clarify that most rigid objects are spread out and not accumulated at a single point. So, like in 4.7, I believe, where we learned about gravitational pull, uh, it's a little bit strange because we assume that the mass is acting uniformly or at one specific point, but we know that's not the case, right? Um, Obviously, you need calculus to further use gravity or further try to find the point. But if you think of the Earth as a sphere, then the center of mass is obviously just going to be at the center. Um, but the point being is that some objects aren't uniform. Some objects are really weird shapes. Um, and basically, these objects can move in a different way. And there's two types of motion. There's translation and rotation. So kind of think of it like your algebra class or a pre-calc class. If there's a person here and he jumps forward, usually you'll see that at this point they'll be like that, and at this point they'll be like that. But you throw like a football, and a football will be rotating constantly. So not only are you applying a force, which we learned before as torque, to rotate the ball on its axis, you're also pushing enough force to, I guess, get it in parabolic trajectory. or in a curved motion, essentially. So rotational motion is also it might occur in combination with translational motion, um, but just note that rotational motion is sometimes called curvilinear motion. One second. So yeah, that's the logic there. So let's do a practice problem, and I'll just make the practice problem because I don't want to read these questions. Um, so we'll have a hinge here. Well, let's say this is a door. And let's say that this is 5 meters wide. If you applied a force of 10 newtons and the torque was 50, um, how much? Oh, I guess. Well, I already gave you the lever arm. How much torque is there? Well, obviously it's just the force times lever arm, which is just 10 times 5, which is 50. So it's 50. 50. The magnitude of the torque is 50. But here's the thing. I don't know why, and I even asked my teacher about this. I don't know. Like, some things don't make sense, and, like, I don't know why they denoted it that way. But a counterclockwise is positive. So this is actually a positive torque, but a clockwise is a negative torque, which is a little strange. Um, not too sure why, because maybe it's because an upwards force is considered positive in most. Um, but this is on the XY plane. This isn't on a XYZ plane, I guess. But I'm not too sure why. But in other words, uh, this way is positive, and this torque is considered negative. So yeah, that's the logic there. Um, a line of action is simply just going to be what. Wait. A line of action is always just going to be following the force vector, essentially. Um, so like the line of action is right here. I mean that's just pretty self-explanatory and such. So yeah. Um, that's it for torque. You can think of torque much. Yeah. So torque is just the amount of force that is being exerted at a specific lever arm. And I think it's pretty intuitive that the closer you get, the less force there is, because we can apply that to real life. And I love application to real life. I guess that's what makes science unique. So